Hi everyone. So in this lecture, I'll very briefly discuss why do we need inductors in RF circuits? Why do we see inductors in RF circuits? So I'll just give a very general overview of an RF system. So most RF systems contain a digital processor. For example, there will be a digital processor which will process the data, and this digital data will then be converted to a analog signal using a DAC, a digital to analog converter. Then this data will be modulated, multiplied by a carrier signal cos omega ct, and then this will be passed eventually through a power amplifier and transmitted through an antenna. This is the symbol for an antenna here, transmitted through an antenna. So we have a power amplifier here, and similarly at the receiver, so for example you have your cell tower, okay, and it radiates power, and eventually your mobile phone terminal will receive this signal. At the receiver, the receiving antenna is going to take the signal in, and then it has to, for example, the received signal would undergo a lot of attenuation in the air. By the time it reaches, it's going to travel a long distance before it reaches the mobile phone. So therefore there will be a significant attenuation in the signal power, and therefore you need to amplify the signal. So that the first stage, as you see, the receiver will be a low noise amplifier. So there are two conditions for this amplifier. We will go about these amplifiers in much detail once we start discussing about the circuit design for the amplifiers. But here, why is it a low noise amplifier is that the signal level is very low because it undergoes huge attenuation before it reaches the low noise amplifier. So therefore, since it undergoes a heavy attenuation before it reaches the low noise amplifier, you need to amplify the signal. At the same time, the noise added has to be very small because the signal level itself is very small. The noise added has to be very small, and also it should amplify the signal. Okay, so these are the two tasks. Now, generally RF systems are what we call as narrowband communication systems. So meaning a low frequency signal will occupy energy around the zero frequency or DC. A high frequency signal, on the other hand, when I say high frequency signal seen by the low noise amplifier or the power amplifier, okay, or the power amplifier, these signals will be occupying a narrow band of frequencies around the carrier frequency Fc or omega c. Okay, so now you need a circuit which has to amplify signals in this narrow range of frequencies. Okay, so either for the power amplification in the power amplifier or in the low noise amplifier at the receivers. Both transmitters and receivers need amplifiers which can amplify signals in a narrow band of frequencies. Now if you look at the conventional amplifiers, the conventional low frequency amplifiers, I'll just take an example of a common source amplifier. A common source amplifier with a certain bias current and a load capacitance CL. A common source amplifier with a with a certain bias current and a load capacitance CL. We saw in the last class that the intrinsic gain of the common source amplifier is GM0, minus GM0 for a common source, but magnitude is GM0. If I plot the gain as a function of frequency, it's going to be like this. So it will encounter a pole at, you can easily find the pole, it will be at 1 by CL R0, and the magnitude is GM R0, and eventually for high frequencies the transfer function is going to be something like this, GM R0 by 1 plus S CL R0. So for high frequencies this will reduce to minus GM by SCL. It will look like an integrator, and the gain here is GM upon, if I take the magnitude of it and plot it, GM by omega CL. So which means the gain reduces as a function of frequency. But for an RF signal, say for example the carrier frequency Fc is somewhere here, and we need a gain in this region, a significant gain in this region. Okay, so for example I'll just take some numbers. GMR0 say is 20, and say we need a gain of say 100. We will have to cascade at least 2-3 stages, but or let me just assume that the gain needed here at the peak gain around Fc for the first low noise amplifier is say 20. How do we get that? I mean, this gain here is going to be at Fc here, it's going to be much smaller than 20, because there is significant attenuation because of the capacitor. So how do we get gain here? I mean, if I want a gain of 20, then all I need to do is GM by omega CL, I need to equate it at omega CCL should be equal to 20. So from that, if I know the load capacitance and frequency, I can compute what is the GM necessary. Now that GM necessary will be, you know that GM we discussed in the last lecture for a MOSFET or a BJT is proportional to the bias current, okay, I bias. So which means if I'll need a huge amount of GM for you to get a gain at its low frequency gain. And now for example, the low frequency gain maybe say 20, FC say is for example 100 times from the pole, then the attenuation will be roughly 20 upon 100. The gain would have been attenuated by 100 times by the time you reach FC. Okay, so which means you need to increase your GM 100 times compared to a low frequency amplifier to get the same gain at FC. I just took an example here. I said that if I assume the intrinsic gain GM into R0 is 20, and it turns out GM by FC, that is omega CCL, is actually 20 by 100. But if I want to make it 10, if I want to make it 20, then I have to increase my GM by 100 times, so that this gets multiplied by 100 and you get a gain of 20. Okay, so my bias current requirements increase significantly. So how do you fix this problem? How does RF circuits fix this problem? They need a gain for a narrow band of frequency. They don't need it for all the frequency range. They just need it for a narrow band of frequencies around a carrier frequency. So one of the simplest ways to do that is, if I take an inductor and put it in parallel with the load capacitor, what happens in this circuit is that this network, we know that the impedance of an inductor starts increasing with frequency and the impedance of the capacitor decreases with frequency. Okay, now we also know that the impedance, when you actually put it in parallel with a capacitor, the inductive impedance has a tendency to cancel out the capacitive impedance. Okay, at the resonant frequency, the impedance of an inductor is j omega L and the impedance of the capacitance is minus j by omega C. And at the resonant frequency, both of them become equal if I choose L such that at the resonant frequency, and I'll choose resonant frequency as Fc. If I choose resonant frequency as Fc, the impedance of the inductor and the capacitor will become infinity at Fc. So what in effect this capacitor is doing is that it's behaving like an open circuit at Fc. So we can see that purely if I plot the impedance of a capacitor without an inductor, it goes like this, around there is a pole at DC. Now by merely adding an inductor in parallel with the capacitor, I have shifted the point where the impedance becomes infinity to Fc. Okay, now the behavior of the capacitor is now the same. What used to happen for a capacitor DC, just an open loop capacitor, just a two terminal capacitor. Now the same behavior gets shifted to Fc, or the resonant frequency. Here I have chosen Fc, where Fc is 1 by 2 pi root LC. It gets shifted to this resonant frequency. In this case it is the carrier frequency. Now if I put this in parallel with the transistor, so what I am going to do is that I am going to put an inductor. I have just introduced an inductor in the circuit and a capacitor in the circuit, and there is also R0, So what's going to happen is that the DC gain of the circuit is 0 because inductor is going to offer 0 gain at DC. At 0 impedance at DC, it's 0. Again at infinite frequencies it is 0. It's going to be GM by SC. It's going to follow the same curve, GM by SC. At low frequencies it's going to be GM into SL. At the resonant frequency, at the carrier frequency, because the capacitor and inductor perfectly cancel out, the only thing remaining will be the resistor itself. Okay, so if I have a parallel R, L and a C circuit, at the resonant frequency these two will cancel out each other and you will be left with only R0. So you are going to get a gain of GM R0 at the carrier frequency. So that way, by introducing an inductor, I am saving power. I don't need to burn like 100 times more current, okay, just to get the gain. I don't need to do that. I just have to use an inductor, an ideal lossless inductor, and resonate out the capacitor. I am just trying to remove the capacitive effect in the circuit at certain frequencies. Okay, so that way I can attain a gain for a narrow band of frequencies. In this, there is a, again we will come to that for how, for what is the range of frequencies for which the gain remains constant. We will come to that later, but theoretically we can do this. Now what happens if the inductor has a finite Q, meaning the inductor is actually, I have assumed it's an ideal lossless inductor, but every inductor in practice will have a finite Q. So if this is L, there is going to be a series resistance associated with it, and there will be a load capacitance. Now in this case we are interested in finding out what is the voltage gain for this circuit. So what I will do here is, because we are interested in finding the maximum gain only at the resonant frequency, we can actually assume that we know that the inductor Q is given by omega naught L upon Rs. This is inductor Q. Okay, so we can represent this, if Q is, I'll assume the Q again is much greater than 1 at the carrier frequency. In this case it is omega C L by Rs. I'm assuming this is much greater than 1. So we discussed that the inductor in, a series inductor with a resistance in series can be approximated to a parallel inductor and a resistor in parallel, Rp and Lp. And we said Lp was Ls into 1 plus 1 by Q square, and Rp is Rs into 1 plus Q square. For Q much greater than 1, Lp is approximately equal to Ls, which is L in this case, it is L in this example. And this here Rs is actually Rs into Q square. And I'll write in terms of Q, Rs into Q can be written as omega Q into omega naught L by Rs. I've written one Q as omega naught L by Rs. So Rs and Rs cancels out. We'll be left with Q into omega naught L. Okay. So in fact an inductor with a series resistance, you don't, either I can give you the value of Rs or I can just tell you the value of Q. That is sufficient. Q already captures losses in a circuit. If Q is infinity, it's a lossless circuit or a lossless inductor. For a finite Q, I can replace Rs, the series resistor, because I've defined Q like this, omega naught L by Rs as Q. So Rs is going to be, for a series inductor, it's going to be omega naught L by Q. So this is omega naught L by Q. A series resistor can be modeled like this. See here I have not used Rs anywhere in the circuit. Q here already captures losses, So that's how we define Q, and I can, instead of series resistance Rs, I can write it in terms of inductor as omega naught L by Q. Now I am going to substitute this value in the circuit. So I am going to have, for Q much greater than 1, the inductor will be same, L is same, the capacitor is C here, and instead of Rp I am going to have Q into omega naught L. Okay. Now if you are asked to find the gain of the circuit at the resonant frequency, this L and C will resonate out and they will behave like an open circuit at the resonant frequency. And I'll also make another assumption that Q into omega naught L, which is Rp, is, R naught is much greater than this. Okay, generally that's the case. Your R naught will be much higher. So you'll be left with Gm into, the gain is going to be minus Gm into Q into omega naught L, or the magnitude of the gain. I don't have to write minus here, simply the magnitude of the gain AV is going to be Gm into Q into omega naught L at the resonant frequency. Now this gain, if you see, this term is not under the designer's control. It's still under the designer's control. It's more of an inductor, depending on the geometry of the inductor and all that, the Q depends upon it. Okay, so this will be fixed. So as a designer, purely as a circuit designer, you have your Gm to play around with. So if I use a good lossless inductor whose Q is very high, then the gain will approximate your intrinsic gain itself, which is Gm R naught. Okay, because actually if you see the gain, it is Q naught WL W naught L omega naught L into R naught. Okay, it comes in parallel with this, because this is your Rp, it is Rp parallel R naught is your gain at the resonant frequency. But now I have assumed R naught much greater than that, so it's going to be Rp. If your Q is very large, then you will get the gain as resonant frequency itself. But if your Q is, less, Q into omega naught L, the inductive losses are such that the Rp is actually less than R naught, then you will have a gain GMQ omega naught L. So here GMQ omega naught L is your gain, And if you look at this gain, this RF gain, it actually depends upon bias current, because your GM is a function of bias current. So here gain is also proportional to I bias into the Q of the inductor. Okay, for example, if I fix the value, because once you know the load capacitance, then the value of L is also fixed, because that gets fixed because your carrier frequency is fixed. Okay, so based on that, I'll fix the value of L. Now for a given value of L, I can have different Qs. If I have large area, I can realize an inductor with very high Q. Okay, so I can have Q under my control, and I bias is also under the control. To get a good inductor Q, it requires good layout practice and also larger area, or you have to burn more power. So these are the trade-offs in RF circuit design, and I've just given a very crude understanding of what is the challenge in designing an RF amplifier at high frequencies. Okay, we will go in more depth once we start discussing about the amplifiers in great detail. Okay, so I'll stop at this point. So here the main point to know from this lecture is that the intrinsic gain, the gain of an amplifier is actually proportional to the bias current and the Q of the inductor. And we use inductors in RF circuits because we need to get high gains at high frequencies. You cannot get those high gains without inductors using just passive circuits alone. Using just amplifiers alone, regular conventional MOS amplifiers alone, because once they are capacitively loaded, they start going to give you lower and lower gain at high frequencies. Okay, so there are so there are techniques to deal with those problems, but this is a very fundamental idea behind why do we go for using inductors in RF circuits. Okay, I'll stop at this point.